Alright. Welcome to this extension 1.7 to 1.8b extension. And in this video, we'll be covering a few extension problems related to cones, frustums, and areas of circles. So as you can see in this packet. Okay, good. So for the first part, we're going to focus on the formula for the volume of a frustum. And what is a frustum? Well, a frustum is a shape that is formed after a cone or pyramid has its upper part cut off by a plane parallel to its base. What this essentially means is, if we were to have a pyramid or a cone, right, I'll just draw something like this, right, that resembles like a pyramid, and we cut the top part off, our resulting figure is going to be a frustum. So it's like this part, or it's this conical frustum. Okay. So in this case, we don't really care about the volume of a pyramidal frustum. What we want to derive is we want to find the formula for the volume of the frustum of a cone. So this shape. And how do we do that? Well, we can start by having a large cone and a small cone. And then we would take the whole area, this whole thing, and then subtract the top part. So we are left with this part, right? And just to repeat, this part is equal to the whole thing minus the top part, subtracted by this part. So we don't want that part anymore, okay? All right. And just to review, the volume for a cone is 1/3 pi r squared h. And we will have to use that in our derivation. All right, let's get started. So the first thing we want to do is we want to look at the relationships between the two heights. So in fact, if we look at the triangular cross section, we're going to get something like this. Right, note that this picture really just comes from this part of the drawing. Right. So this would be the radius, the top radius, this would be the bottom radius, this would be like the slant, this part would be like the slant height, right, and this part would be the height. So if you've done similar triangles before, we can actually say that this triangle and this triangle are similar, right? And if you don't know what that means, what this basically means is that if this is h1, this is h2, we have that h1 over r1, the proportion is equal to h1 plus h2 over r2. This proportion is the same. Now, if you don't really understand why, it's okay. You'll learn it in a future unit, but this is just a heads up on similar triangles. So in here, what we want to do is we want to express the full height as h, and we want to derive that in terms of what? Yeah, and we want to derive that in terms of r1, r2, and the top height, which is small h. So we use similar triangles saying that r1 over r2 is equal to h over h, right, small h over big H. Oh, actually, it'd be better if we set this part as h, because in the end, we want the h to be this section. Right, so this will actually be h minus h. And then through some simplification, we get r2 times h minus h equals r1h, and then r2h equals r1h plus r2h. Wait, what am I doing? Let's see. r2 times h minus h is equal to r1h. That's correct. And then what we want to do is, oh yeah, R2H equals R1H plus R2H because we expand and then move this part over. And then we get H is equal to R1H plus R2H over R2. Or, sorry, give me 1 second. Let me see what I did wrong. Yes, RH. Oh my gosh, this is actually big H. This row and all. Yeah, and then everything else should be correct. R2H minus R2 small h equals R1H. So if we move this over, if we add R2H to both sides, we get R2H equals R1H plus R2 small h, and then some simplification. We get H is equal to R2H over R2 minus 1. Yes, this is correct. And this seems like a really nasty formula, but we will have to use it later when we're deriving the volume of a conical Frustum. Right, so now you might not really know where we're trying to go for. I'm going to kind of minimize this a little. Put this here. But ultimately, to find the volume of the Frustum, we want to take the larger cone, and then subtract that by the volume of the smaller cone. We want to take this part, this whole thing, minus this portion. And the larger cone can be expressed as 1/3 pi r squared times big H, while the smaller cone can be expressed as 1/3 pi r squared times big H minus small h. And then, if we take some of the things out, this would be 1/3 pi r I should subscript this. This first part is the R2 because it's the larger one, and the second part is R1 because it is the smaller base and the larger base. So we can take out 1/3 pi. We can take out 1/3 pi here, and then we would get R2 squared h minus R1 squared h minus h. And then with some more simplification.
So now, what would you do to get this massive next square and move the square?
Right.
Yeah, so you add that number, which is still a big number, and then you have to add
Again, all we're doing is simplifying here.
whatever that strategy is. So let's just do that real quick. We have 3, 5.
Okay. Move this over. And then after this, we have a really smart trick here. R2 squared minus R1 squared. This looks like a difference of squares. Right? So what we do now is we plug H in. And then we use the difference of squares formula for R2 squared minus R1 squared. So we get this. And then h plugging in would just be this thing. So we would just say R2h over R2 minus R1. And then we still have to add R1 squared h. And then what you can see is that R2 minus R1s cancel. So we are only left with 1/3 pi R2 plus R1 times R2h plus R1 squared h. And with some simplification, which simplifies to this. We can just take the h out here, right? Sorry. Plus R1, R2. And this is exactly the same formula as this. The only difference is that instead of R1 and R2, the big base, the radius of the big base is big R, and the radius of the small base is little r. But in here, we just denoted this as R1, and this is R2, so it is exactly the same. And this is our final derivation for the formula of a Frustum. Okay? So let's do some practice with this. Right, so as you can see in the proof, there are two ways really to find the formula of Frustum. The first way is through this formula, and the second way is through a method that I call completing the cone. So let's try this out with this problem. So first of all, let's try to complete the cone. So we are given a Frustum like this, right? Or maybe I should just copy the shape over. Right, we're given this Frustum. What we want to do is we want to complete the cone. So we want to put it up here like this, right? And then here we have a height of 5. Why? Because these two triangles are similar. Meaning that 6 over the whole height, right, if we were to set this as h for now, 6 over the whole height is equal to 3 over this part of the height, right? 6 over x plus 5 is equal to 3 over x. And then, with some simplifications, we get x is equal to 5. Okay. Yeah, so after that, shoot. Shoot, it's not working. Okay. So after you know x is 5, the process becomes very simple. We have the large cone, which is 6 squared times 5 times 1/3 times pi, of course, right? Because 1/3 pi r squared times h, and my bad here, the h is actually 10. And then we want to subtract that by the small cone, which is 3 squared times pi times 5 times 1/3. Again, 1/3 pi r squared h. Right, 1/3 pi r squared h. So and then we get a final answer, or by simplifying, we can get that this is equal to 120 pi minus 15 pi? Did I get this right? Yeah, 15 pi. And then this is equal to 105 pi. So you get 105 pi as your final answer. And you should, and we now, because we know what the formula of the volume of a Frustum is, we can instead use the formula. So V would not just be equal to 1/3 pi h, and h is 5 here, right? Because this is h. And then we multiply that by r squared, little r squared, plus big R squared plus their product. So we get this. 18. $73. Is it 73? 25 plus 18. 63. And then these two actually cancel, right? So when you're doing calculations like this, be cognizant of the things that cancel in order to make your process easier. Which you get the same answer, 100.05 pi. Right, and these two answers match, so we can confirm that we did it correctly. And this is a really, okay, this problem is a challenge problem, but I think it's really, really interesting. So remember in a previous lesson how you would revolve a line across the x-axis to form a cone? Right? This would actually form a cone. But what if, instead of rotating a line passing through the origin, rotate a line that actually has a higher y-intercept, like this? Well, now when we reflect it across the x-axis, we would actually form a frustum. Right, so I want you to kind of intuitize that. Like, originally, if it was in the origin, we would form a cone. But now, when it does not pass through the origin, we would actually form a frustum. Right, and we want to find the volume of this frustum through the equation of this line. So what is the equation of this line? The equation of this line is y equals 5 over 3x plus 2. So let's draw that real quick. Hey,
你在外面？
我在录视频给他的课。
你在录视频？
对。Okay. So if we were to reflect this across the x-axis, right, we would get a frustum like this. Right, and then we want to do this between x equals 0 and x equals 3. So this point would be what? 0, 2. This point would be when x is equal to 3. So we would have the point 3, 7. And then over here, because it is reflected across the x-axis, negate the y and negate the y. Right? So what does this give us? This gives us a frustum. That was a terrible frustum. With what characteristics? It has a top radius of 2. It has a bottom radius of 7. And it has a height of how much? It has a height of 3. Why is the height 3? Well, if we go from here to here, we're going from 0 to 3, which is a height of 3. Okay. And then through the volume of the frustum, v equals 1 over 3rd pi times h, which is 3, times 2 squared plus 7 squared plus 2 times 7. You should get a final answer of 67 pi. And yes, that was intentional. You're welcome. It's a number I really love. Okay. But what about if I do this? What if I choose to revolve y equals 5 over 3x across the x-axis, but I want to find the volume between these two values. And right now, you might think it's kind of weird why I chose these two numbers, right? I didn't even choose integers, I just chose some random fractions. But you'll see something very interesting happen. So, again, we can draw our y equals 5 over 3x line. And then this is x equals 6 over 5. And this is x equals 21 over 5. And then again, we want to rotate this around the x-axis. So again, we would be forming, guess what? A frustum. Right? And then, this is where the interesting thing happens. What point is this? This is the point 6 over 5, comma, 6 over 5 times 5 over 3, which is 2. This is the point, what? 21 over 5, comma, 21 over 5 times 5 over 3, which is 7. Why does 2 and 7 look the same? Why do they look so familiar? Well, didn't we just have a problem that had 2 and 7? Right? And if we really draw the frustum out, you would find that the top radius is equal to 2, right? This part is equal to 2 because you're going from 2 to 0. Bottom radius, again, is equal to 7. And what is the height? The height is 21 over 5 minus 6 over 5, which is 15 over 5, which is 3. And then again, we use the same formula. Get the same answer of 67 pi. Interesting. Now, if you look at these two problems, they don't look the same. We're not revolving the same equation, and our limits are not the same. So why do we, in the end, get the same frustum? Now, this goes back to what I explained previously about how you can complete the cone or use the formula of a frustum. And this is kind of a graphical way to represent it. What we did in the first part was we chose to get the frustum directly. Right. And that's totally okay. We chose to revolve a line across the x-axis to get the frustum directly. But on the other hand, what we did in the second was, okay, we decided to move this over a bit. Shoot, my bad. We decided to move this over and then complete the frustum to form a cone. And this is exactly why I chose the numbers 6 over 5 and 21 over 5. I chose those numbers so that I could perfectly complete this frustum to form a cone. And then, because we are essentially getting the same frustum, right, they have the same area. So, to summarize, we are essentially using the same frustum in part 1. We directly form the frustum. In part 2, we cut off the top part of a cone to form a frustum. Right, does that make sense? Yeah, and I think this is a really interesting extension. Yeah, because frustums are pretty cool. They're not really covered in math classes. And I think it's pretty interesting how we can also kind of think about it graphically. Yeah, and a cool poem. Do we still have time? Let's see. 52. Okay, we have 18 minutes. A cool poem that I want to share. It's a very funny poem. Come, every frustum longs to be a cone. and every vector dreams of matrices. Right. I think it's a really interesting poem. If you want to see the full poem, feel free to click this link. It's very mathy though, like a math nerd warning. Okay. Now let's move to part 2. AMC extensions. So the first question, we want to find this shaded area. How do we do that? Well, we could, to find this area, we could find the total area and just subtract off this little bit. But how do we find this little bit? Now we have to use this circle. What we want to do is we want to find the area of this sector, this whole sector, and then subtract off this triangle, which leaves us with just this portion. Okay. So, a trick here, right, that I kind of just did without telling you guys is in problems related to circles, you often want to connect points to the center, right? And important points to the center. You don't want to connect random points because they can often give you some extra conditions and help you solve the problem. And because these two lines are actually radii because they connect a point from the outside to the center. So these two lines have a length of 1, right? Diameter is 2 means radius is 1. So how would we solve this? Let's say this area is S, right? The radius of this small sector. S is equal to, and we know that this is what, 60 degrees, right? Yeah, this part is 60 degrees because it's an equilateral triangle. So the area of S is equal to the sector area, which is 1 squared times pi, or let's say pi r squared times 60 over 360, this area, subtracted by the area of the equilateral triangle, which is root 3 over 4. Now, if you don't know where root 3 over 4 came from, we just drop a height here, and then everything, and then you can calculate it that way too. R is 1. So this just becomes 1 over 6 pi minus root 3 over 4. And this is this area. But we're not looking for this area. We're looking for the shaded area. So the shaded is equal to the area of the half circle minus this S. The area of the half circle is 180 over 360 times pi r squared, and then that is equal to half pi 1/2 squared. 1 over 8 pi, and what is our S? Right, our S, just plug it in here, and then you should get a final answer of root 3 over 4 minus 2 over 48 pi. Or, I'm going to simplify, 1 over 24 pi. This should be your final answer. Okay. Last problem. 2017 AMC 12B, number 14. This problem actually goes back to the idea of Frutsum. So an ice cream novelty item consists of a cup in the shape of a 4-inch tall Frutsum of a right circular cone with a 2-inch diameter base at the bottom and a 4-inch diameter base at the top, packed solid with ice cream. So let's draw a picture for this first, okay? So what does this include? There's a cup, so it looks something like this. And then this is 4-inch tall, so the H here is 4. 2-inch diameter base at the bottom, and 4-inch diameter base. Oh yeah, it's a 4-inch diameter base. So the radius would actually only be 2. And the bottom radius really is only just 1.
This is cool, and you get lots of cool tricks, and you're doing squares quickly, and you're doing your visibility rules, and you can do all of this awesome numerous.
Yeah, so after we draw a diagram, this problem becomes really easy because we're just plugging and chugging the formula in. So we get 1/3 pi times 4 times r squared times small r squared times r times r. Right? 7. So we get an answer of 28/3 pi. Is this correct? Let's check.
Again, this is so astonishingly fast. Usually I'm pissed off at grades 5 through 8 for not having done it. But what were you doing the other stuff for? This is so much better. Why don't you do this?
Oh, my bad. We still have to add, right, this is not the full thing. And then we still have to add a cone on the top.
Shrink, solve, and scale.
And this has height 4 inches. So this is only part 1. And part 2 would be this cone. So the formula would be 1/3 pi r squared times h. So 16/3 pi. And adding those two together, you get 44/3 pi. And I'm not sure if this is the correct drawing because I'm good at math, I'm not good at reading. Let's check. Base at the top. Yes, that's correct.
You're doing BC?
It's like I'm making a video guide for
Oh.
yeah. Okay. Yeah, and that's really all for this one. I think there's one more problem that I missed in the middle, and that's going to be in another video guide. I'm really sorry for making you jump between my videos. Yeah, but I think that's all. Yeah, really appreciate you watching this, and see you in the other video. Thank you.